Today I'm going to show a demonstration of how we can use topology optimization for systems like a slider crank mechanism. So quite often when we design a system, it does something like this. We see that it's severely vibrating, and so we want to come up with a new design that allows us to improve this performance. In order to do this, we have come up with a workflow to perform topology optimization based on a flexible multi-body model. In this workflow, we combine multiple toolboxes and toolchains that we have developed over the years within DMMS-D and within Flanders Make. So first of all, we have our MBRC toolbox that allows us to define and simulate flexible multi-body systems. Next to this, we can interface with the mesh extraction and topology optimization toolbox to ensure that we can set up a topology parameterized description of the components in the system. Next, we use an MBRC plugin to obtain the adjoint derivatives based on the multi-body simulation, such that we can get very accurate and very fast gradients with respect to our different design variables. Once we have this problem set up, we can continue to the actual optimization in which we update and evaluate the multi-body model. We run the adjoint solver, and finally we use the open source framework IP-opt as an optimizer in order to improve our designs and to come up with the design results. Now this is the theory. Let's have a look at what this looks like for the actual implementation. So let's have a look at the MATLAB toolbox here. So first of all, what we need to do is we need to load the necessary toolboxes. So this framework is first of all based on the MBRC. So MBRC is a flexible multi-body toolchain that we have developed at DMMS, and it allows us to simulate a wide range of mechanisms. Besides this basic toolbox for MBRC, we need the plugin to compute the adjoint gradients. And we need to have two additional toolboxes specifically for the topology optimization. One of them is in order to interface with Nestran and extract element properties from Nestran, such that we don't have to redefine all the elements ourselves in the toolchain. And the other one allows us to efficiently set up the optimization problem and evaluate the stiffness matrices and so forth. Once we've loaded these toolboxes, we can define the case that we're looking at. So in this particular case, we're setting up a simulation with a driver. That means that we're determining the input motion. We're not just applying a torque. And we're having here, for example, a quadratic increase of the crank angle. We store this in variables. And of course, we can see that here, for example, we have this quadratic increase in the angle, and we have this constantly increasing velocity. Now, from this setup, we can first of all analyze what's going on with the original system. So here I can set up a simulation where I define my problem, I define my system, and I define as an input file for the crank this original crank mesh. So it's a mesh that I set up in NX. And here we define the multi-body model. So we have a bunch of variables, we have elements, so those are all the bodies, all the joints that are part of the mechanism. So we see we have the ground, we have a base block, we have a motor support body, we have a support on the right, we have the motor, we have the motor shaft, which also contains the inertia of the rotating part of the motor. We have our crankshaft support on the right. We have our actual crank. So our crank in this case, it's coupled to not a regular body as we have here, but it's coupled to an optimization body, which will also allow us to then afterwards, for example, change the parameters as we defined it as a topology optimization body. And then we have the connecting rod, which is also finite element body, deformable. So we have to define a mesh input file. So this is regular Nestran input format. We have a slider body, we have the track as a body, and so you see several of these bodies have been defined as their CAD components. We can add the joints that connect all the different bodies together. Some of them we call joints, some of them we call constraints, but they're practically the same thing. So after we defined all this, and of course there's quite a few as we have included a lot of bodies here, We add a motor, torque, or a driver. So in this particular case, we have a driver which describes the motion of the motor shaft. And we set up our entire system as a flexible multi-body model. We can then run the simulation. I'm not going to do it here live. It takes around 2 minutes, but I only have around 10 minutes for my entire demo, so that would take us too far. But so we first run this for the original system, which gives us a response of this form for the speed up. So we see initially everything is going pretty smooth, but as we go faster and faster, and it's a bit exaggerated here, but we see that all the components start to shake as a result of unbalance, which is similar to the kind of vibrations we saw in our experimental setup. Now, this is the original problem. We say, okay, we want to go to a better design. So we define a new body or a new system where actually we have where we input our new body, which we can use for the optimization, and that gives us a result that looks something like this initially. So we set up an entirely circular domain for the optimization. I can maybe quickly zoom in here. You see that there's a completely circular mesh here. So this is all the room that we might have available in order to do our design. So we could also have material on this side that is added in order to get a properly balanced design. Now the question is, can we find where we want to add material and where we want to remove it in an automatic fashion? So yes, we can. First, we need to set up from the parameterized description of the mechanism an optimization problem. For that, we use this measurement object, in which we say that actually the objective that we're trying to minimize is the deflection energy or the deformation energy in the component that we're optimizing. We can set our scheme in order to compute the gradients. We actually have a continuous adjoint solver and a discrete adjoint solver. In general, our discrete adjoint solver works better, so we select the discrete adjoint solver to solve the problem. And we can set up a number of parameters for the forward solver, so the forward simulation that we're going to run. So basically these parameters are consistent with the simulations I've ran before. This allows us to fully set up our optimization problem, and then basically we can run some additional masks, for example, for our design. So in this particular case, we knew in advance that we wanted to have a design which we could construct through what is the method called again? Spark erosion. So basically it needed to be all parts that we could just cut out. So we couldn't have this kind of typical complex structures. So we defined that all the cutouts have to be in the X direction in order to ensure that it's a producible design, and we can apply a mask to the optimization problem such that several parameters are coupled together. In the next step, we need to set up the IP-opt optimizer. So there's a number of parameters here. So we need to define, of course, our objective function and our gradient evaluation. We have some settings like the maximum number of iterations, the tolerance that we're looking for. As we cannot provide an exact Hessian, we actually use a BFGS approximation. And actually, as most of these iterates turned out to be very conservative, we can even just accept every trial step such that we don't need to do a full line search every time, which saves us quite a bit in computational load. So after setting up this problem, so this is very general, there is nothing much here that is specifically to topology optimization. We can run IP-opt, so the regular call to the IP-opt function for MATLAB whenever we have some auxiliary data in order to evaluate our problem. So again, what do we get? Well, we get this kind of result where we see the design evolve over time towards something that looks like it might be a bit balanced. But is that the case? So let's see. I'm going to cheat here a bit again. Obviously, I didn't actually run it. That would have been a bit too fast, but so I ran it in the past. So I got out the result, and I can again evaluate our new design. So what we can do here is it's interesting because we can on the one hand set up our multi-body model, but here we can actually also write out a mesh file for the newly obtained design, such that we can actually load in the measure that we obtained in a general format, a general Nastran format that we can again read into NX. So if I run this. So here I generate a new file for the mesh. I can run the simulation with this new file. Let me update this, it had to be this. We can run the simulation and we can again visualize the design, and so we see that the design now looks very different from what we had before. We still have vibrations, but they're actually reduced with before. Now the proof for this kind of stuff is in the pudding, or is in eating the pudding. So what we did is we loaded this design into NX, where we could manipulate a bit further to ensure that everything is properly defined. We could extract it and then we can go towards the actual manufacturing of the part. So we took this part to our spark erosion machine. We manufactured a component and mounted it in a new setup such that we can do a back-to-back comparison. First, we start the older machine at 50 RPM. We see that we get some vibrational levels out of it. But when we increase to 60 RPM, we see a dramatic increase in the measured accelerations on the system, much more than the 20% velocity increase would suggest would happen. So then we go to our new design. We again started at 50 RPM. We see that we get similar-ish vibrational levels, but when now we accelerate to 60 RPM, we see that we get much lower vibrational peak levels than we have in the old design, which is of course the entire goal of this exercise. So it seems that at least the approach has some of the benefits that we expected it to have. Further tests still needs to be done because of course these machines are not perfect, but so if you have any questions or interest, please contact us.